5.2 one-to-one and inverse functions, a section with quite a lot of theory in it. You do need to know a couple definitions here and there, and the first one you sort of need to be familiar with is a one-to-one function. So it says here, a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function f, then f is one-to-one if f of x1 does not equal f x2. Now here's a picture of a function. Now let's see if it fits the one-to-one definition. So x1 and y1, x2 has a y2, x3 has a y3, so it is a function. And then is it one-to-one? Well, let's see here. So one-to-one means that we are looking to see that we do not have any repeating y values. So no repeating y values. So no repeating y's. So that means that this one is one-to-one. Alright, how about over here? So is it a function? Yes. Okay, every x only has one y. However, over here we have a repeating y. And since two x's share the same y, this one is not one-to-one. How about the last one? Well, we don't have any repeating y's, and this is why you have to be careful with. However, we do have a repeating x here, so you cannot say that this is a one-to-one function. First of all, check to see if it is a function. This is not a function, and it can also, by definition, not be a one-to-one function. Okay, let's move over to onto a different type of example. So, what if something like this is given? Well, let's just check. Do we have repeating x's? No. So every input value is unique. Is every output value unique? No. Right there, both John and Andy apparently drive a Pontiac, so this one is not one-to-one. Okay, how about here? Now let's check your x values first. So we have unique x's, 1, 2, 3, 4. So yes, no repeating x's. So it is a function. Let's check your y's. So 5, 8, 11, and 14. No repeating y's as well. So then this one would be one-to-one. Okay, and that leads us to a new kind of test, a horizontal line test. And a horizontal line test is what is designed to determine if a function is one-to-one. If you draw a horizontal line and it crosses in more than one spot with the function you're looking at, then it is not one-to-one, because it implies that x1 has a y value and x2 shares that y value. Not one-to-one. It's really easy to work with. Right? I can only get one intersection at a time. One-to-one. Over here, this horizontal line has 1, 2, 3, 4. If I had drawn it horizontally, then it would have had 4, so this one would be not one-to-one. Okay, that also leads us sort of to a little theorem, and it says that a function that is increasing on an interval I is a one-to-one function in I. What they mean with that is the following. If I look at a function, okay, for example, let's just look at, what do I want to look at? Let me cheat for a moment. So we're going to draw a function here. Okay, so this function is one-to-one because it passes the vertical line test for all x's, for x is an element of all real numbers. Okay, this whole function is increasing, so it's increasing over its entire domain. But I can also have, that's a cubic function probably, right? I can also have a cubic function, maybe that looks a little more like this. So I have a pronounced hump like this. Okay, definitely not one-to-one anymore. However, if I divide this into its little chunks like this, so on this intersection over here, if I'm looking from here to here, on this intersection it's only increasing, right? So it's increasing on that part of the function. Well, if I only look at that part of the function, then do I have a one-to-one function? Well, let's just check. So I can carry that with me. Would that be one-to-one? And I would say that this little chunk here at this point became 1 to 1. And you can do the same thing with all the other parts as well. And that just means that there, that's about as good as I'm going to get it back. And you can do that with the other parts as well. You could look at only, so we could look from here to here, so the whole function is decreasing, and on this part it's 1 to 1, so because you're only considering this line over here, and then the same thing over here, it's only increasing, so every one of these will only intersect once. Now that's useful when we want to work with functions that need to be 1 to 1, but maybe over its entire domain they're not. So this intersects, or this function that I just sort of drew over here, it's 1 to 1 for the following intersections, or for the following sections. So let's put a tick mark here, let's put a tick mark there and there. So from a negative infinity, so if that's at a -1 to -1, it was 1 to 1. And then from a -1 to 0, it was 1 to 1. And then from 0 to infinity, it's 1 to 1. Okay, so the whole function is not 1 to 1, but taking it into chunks, it would have been. Okay, then here's the reason why we spend time on 1 to 1. For us to be able to look at a function and to talk about the inverse of a function, we need to make sure that we have a 1 to 1 function. And the reason for that hopefully sort of feels right or makes sense. If the function is 1 to 1, so that every x has a y that is unique, okay, and then an inverse would be when you swap your x's and y's. So now instead of calling these the y's, these would be our x's. Then they map back into unique values. So now if I look at y1 and I say, okay, let's look at y1 as my x, would that give me a unique value on the other side? Well, in this case, since the function originally was 1 to 1, it would. But if you look at a function that looks like this, where this is y1, and then x2 would also give you y1, then if both of these map into, if you now swap it around, then you would have y1 sometimes would be worth x1 and sometimes would be worth x2. Now if that's the input, then we have different y value or different output values for the same input, and that would violate our function definition. So inverse function and 1 to 1 functions are sort of tied together. And the other thing that you need to do to learn out of this in terms of weird stuff is that that's the notation for an inverse. Okay? Okay, let's go look at an example. It usually works a little easier in the example. So let's find the inverse for the following function. So the domain is a student, and the range represents the make of the student's car. State the domain and the range of the inverse function. Okay? So for inverse, we're going to swap x and y. So my inverse function would look like this. So the inverse of this, the x value becomes the car. So it would be a Saturn, Pontiac, a Honda, and a Chrysler. And then the output, or the y values, would be the student. So if you see a Saturn, then Dan would be the student. If you see a Pontiac, then John would be the student that's associated with it. The Honda would mean that Joe is visiting somewhere, and if you see a Chrysler parked somewhere, that means that Michelle is the driver. So that would be the domain of the inverse, and then this is the range of the inverse. Swap your x's and y's, swap domains and ranges. Okay. What if it was given to you in this form? What if we were given a function in set notation? Well, state the domain and range of the function and its inverse. Alright, well, the domain for the function would be 1, 2, 3, 4. The range of the function would be 5, 8, 11, and 14. How about the inverse? Well, we'll just cheat. The domain for the inverse is the range of the original. So 5, 8, 11, and 14. And the range of the inverse is the domain of the original. So 1, 2, 3, and 4. Okay. So what I just tried to show you is being presented here in terms of pictures. So the domain of f gives you a range of f. That range becomes the domain of the inverse, and the domain of the inverse delivers you back into the range of the inverse, which is also the domain of f. So you do something to the function, and then the inverse undoes that, and you're back at square one. And that's really a pretty good definition for what an inverse is. An inverse undoes the effect of the original function. And that's basically what we're seeing here as well. If we take an input and we apply f, we get a function value. And then if we take the inverse of that function value, you're back at square one. You're at x. For example, if I take 3 and I multiply by 2, I end up at 6. The inverse of multiplying is dividing. So if I divide by 2, I am back at 3. If it's an inverse for us in algebra or in our class in Precalc, then it does have to work both ways. If you take a input value and put it into the inverse, and that gives you a value based on that inverse, and then if you take the original function and shove it back into there, then you're back at square one. So that's basically all that this is trying to say, is that to confirm an inverse, okay, it, meaning finding the value and then seeing where you end up is, it has to work both ways. Okay? So verify that this is an inverse of that. So let's see. See if we can make it happen. So let's see what g negative 1 of x really gives you. So now we're sticking the inverse of g into g. So this is x cubed. Well, that's the third root of x minus 2. That's what the inverse is, right? It's the third root of x minus 2. We're going to put that in there, we're going to cube it, and then we're going to add 2. And what should come out of here is, well, see if you can guess it sort of. So if we take that, x minus 2 plus 2, we end up with x. And that's what we want. Okay? That's what this is saying over here. If you start with the inverse, put the original into that, you should get x. And we actually did this one. We took the original function, we shoved the inverse into that, we end up with x. And then I do the same thing over here. Let's see, we're going to start now with the inverse, and we're going to put the original function into that. So we're going to do x cubed plus 2 into there. So that would be the third root of x cubed plus 2 minus 2. That's just the third root of x cubed, which is x. So here it seems to work. Now I've sort of purposely skipped over the whole domain question here. So let's make sure that domains are working here. So this domain for a cube is all real numbers, and the cube root is also all real numbers. So I don't have any domain issues here. So this function here is indeed the inverse here for all x's. Okay? Alright, so how about here? For what values of x is the inverse, is this truly the inverse? Well, let's check first of all that it works. So using the original function, we're putting the inverse into it. And so what do you end up with? Well, 1 over, let's see, 2 times 1 over 2x minus a half plus 1. That's 1 divided by the 2, this 2 and that 2 cancel. So that leaves you 1 over x. And then a half times 2 is 1 minus 1 plus 1. So that's 1 divided by 1 over x, so that is x. Okay, am I allowed to do that? Well, let's check. I know that x cannot equal 0, because the function doesn't exist here for the inverse, right? And on this one, we have 2x plus 1 can equal 0, so that means x can equal a negative 1 over 2. So this is true, for all x element of the real numbers except x cannot equal 0 and a negative 1/2. Okay? Did I do that right? I don't think I did that right. Let's see, we just found a composite, right? So on the composite, I need to first check this one. So that is right. X can equal 0. And then you look at the result, and this one works. So I have to correct myself there. You cannot use 0 because the inverse doesn't exist at 0. But as long as the inverse exists, you end up with x over here. And x is this one works for our real numbers. So I have to change this a little bit. So I really don't care about, I don't need this one. I don't need to check that one. And this is the difference between what we've done in the past and then now what we're sort of dealing with in terms of composite functions. With an inverse here being the way that we check it through a composite function. So you check the one that you plug in, and you check at the end, and that's it. So let's see if I can do this right. So what about the other way? So I'm going to plug f of x in 2x plus 1, and that's going to go into 1 divided by 2 times 1 over 2x plus 1 minus a half. So that is 1 divided by 2x plus 1 minus a half, which is 2x plus 1 divided by 2 minus a half. That's actually a common denominator, so that's 2x plus 1 minus 1, that's 0, and 2x divided by 2, that is x. Okay, let's check what that is true for. So over here, this one has to exist for this to work. So 2x plus 1 cannot equal 0. So that means x cannot equal a negative 1 over 2. And this one is always true, so this will work for all x's that are an element of the real numbers, except x cannot equal a negative 1/2. Now this one actually did do it right. Sorry if I confused you there earlier, and like you see, I make some small mistakes in this as well, so just try to be careful and be aware of what you're trying to do in here. So in this case, we were trying to find a composite function, and that means you check what you plug in, and that means you check what comes out. Thanks.